the expression for the work done during an expansion, right? So so we will have just a recap of last class. Okay, so as you know that heat is nothing but what? Heat is the form of energy, right? So heat always flows from when there is a difference in temperature, correct? So the sign convention is nothing but when the heat is transferred from system to surrounding, it is taken, the heat is taken as positive, whereas when the heat is transferred, when the heat or energy is transferred from surrounding to the system, the heat is taken as negative. Coming to the internal energy is nothing but the sum of the kinetic energy and potential energy of the constituent particles of the system, so which is denoted by U. So U is equal to kinetic energy plus potential energy. So the sign convention for that comes out to be, so when the internal energy increases, we take U as positive. When there is a decrease in internal energy, we take U as negative. Coming to the work done, so the expression for work done has been taken during an expansion, right? So what happens when the gas is allowed to expand? What happens? It exerts the pressure, or it exerts the force on the piston, so that the piston moves in the upward direction. So that force exerted by the gas molecules on the piston is given by F is equal to Pa. So if you consider dx as the displacement of the piston, so the work done comes out to be as force into displacement, that is dw is equal to F dx. So since this F is equal to P into A, right? So F is equal to Pa. So dw can be written as Pa dx. So A dx is nothing but what? So A dx is nothing but the volume, increase in volume. So hence we can write dw is equal to pdv. So where A dx denotes the increase in volume. So hence the expression for the work done comes out to be dw is equal to pdv. Alright. So next we just went through about this first law of thermodynamics. So first law of thermodynamics is regarding the conservation of energy. So the statement goes like this: the amount of energy entering the system will be equal to the increase in internal energy of the system, and some of the energy will be leaving the system in the form of work done by the system on its surrounding. So if you consider dq as the heat and du as the internal energy and dw as the work done, so the equation comes out to be as dq is equal to du plus dw. Okay, I think till here, till the mathematical equation of first law of thermodynamics we just went through in the last class, I think, right? So next, coming to the applications of the first law of thermodynamics. So the first law is nothing but, I mean, the first application, first law of thermodynamics is nothing but isothermal process. Okay, so I'll just read out that in an isothermal process, temperature remains constant. If the system is an ideal gas whose internal energy du depends only on temperature, the internal energy remains constant. That is, du is equal to 0. So the first law of thermodynamics can be written as dq is equal to du plus dw, or dq is equal to dw. Okay, so in an isothermal process, okay, the temperature of the system remains constant. Okay, so when the temperature of the system is constant, okay, so if T is equal to 0, so what happens? As you know that U is nothing but what? U is nothing but the internal energy. Internal energy is completely dependent upon the temperature, right? So if T is equal to 0, so what happens? There is no change in internal energy. Hence you can write du, that is, du is nothing but what? It is the change in internal energy. Change in internal energy will be nothing but equal to 0. Okay, so hence according to the first law of thermodynamics, if du is equal to 0, hence you can write dq is equal to dw. Okay, so this is regarding the isothermal process. In the isothermal process, the temperature of the system remains constant. Okay, so if the temperature remains constant, the internal energy also remains constant. Okay, so the change in internal energy can be taken as 0. Okay, so hence dq will be nothing but equal to dw. Hence, you can conclude that heat supplied in an isothermal process is used to work done against the system. So, what happens when the internal energy increase, when you supply the heat? Okay, when you supply the heat to the system, what happens? The entire energy will be utilized to do the work done. Okay, the work done by the system against the surroundings. Okay, so examples has been given there: boiling of a liquid and melting of wax. Okay, so next, coming to adiabatic process. Adiabatic process is nothing but where no heat energy enters or leaves the system. Okay, so the entry and exit of the energy is restricted. Okay, so the entry and exit of the energy has been restricted. So that means that you can take dq is equal to 0. Okay, so dq is nothing but what? It is the amount of heat, right? So dq is equal to 0 you can take. So hence, if dq is equal to 0, the first law of thermodynamics, mathematically you can write that one as du is equal to minus dw. Okay, so du is equal to minus dw. So that means that when a gas expands adiabatically, okay, it is positive, therefore du must be negative. That is, internal energy of the system would decrease and gas will be cooled. So what happens here is, as you know that when the gas expands, okay, consider that a system encloses an ideal gas. Okay, so if you allow the gas to expand, what happens? The internal energy of the gas decreases, right? So according to the sign convention, the decrease in internal energy is taken as negative, right? So hence, you can write du is equal to minus dw. Since dq is equal to 0, the first law of thermodynamics reduces to du is equal to minus dw, or vice versa. Okay, so this is regarding the adiabatic process. So some of the examples has been given there. So bursting of an automobile tube inflated with air, propagation of sound waves in a gas or mixture of gases. Okay, so these are the two examples. So next, coming to isochoric process. So coming to this isochoric process, when the volume of a system is kept constant, dw is equal to 0. Okay, so as you know that, what is this dw? First of all, work done, we have derived the equation, right? I mean the expression for work done. So dw is equal to nothing but pdv, right? dw is nothing but, that is nothing but equal to pdv. So this work done depends upon the volume. Okay, so since in the isochoric process, what happens? Volume is kept constant. Okay, v is equal to constant. So if v is equal to constant, the change in volume will be nothing but equal to 0, right? So since the dv is equal to 0, so according to the work done expression, that is dw is equal to pdv, hence dw will also be equal to 0. So hence you can conclude that work done is also equal to 0 in the case of isochoric process. Okay, so hence the first law of thermodynamics can be written as dq is equal to du. Okay, since dw is equal to 0 here, dq is equal to du. That means that whatever the heat is absorbed by a system at constant volume, it will be entirely used in increasing the internal energy of the gas. Okay, there will be no work done. Since the volume is constant, so what happens? The piston cannot move. Okay, so hence, since the piston cannot move, what happens? Whatever the heat is absorbed, it will be entirely used in increasing the internal energy of the gas. Okay, so that is regarding the isochoric process. So next, isobaric process. In this process, pressure is kept constant. Since the volume can change, the gas expands and work is done. Thus in process, du and dw are non-zero. Okay, so here what happens? We are keeping the pressure constant here. Since the pressure is constant, so what happens? The volume can change, right? So since the volume can change, so what happens? The gas can expand. Correct. When the gas expands, what happens? The work is done. Correct. So hence, in this isobaric process, So in this isobaric process, you can conclude that du and dw are non-zero. Okay, du is not equal to 0, whereas the dw is also not equal to 0. So hence the equation of first law of thermodynamics remains the same. That is dq is equal to du plus dw. Okay, the example for that is nothing but heating of any liquid at atmospheric pressure, heating of a gas at constant pressure. So these are the some of the applications of first law of thermodynamics. Okay, so just go through all the four. Okay, just go through for a few minutes. In case if you have any doubts, you can let me know. So in case if you have any doubts, you can ask. All the four applications of first law of thermodynamics are important. Okay. Okay, fine. Any doubts? Apart from Ganesh Ray, I didn't get a reply from anyone. Any doubts regarding this four process? Okay, fine. So next is regarding the work done in an isothermal process. Okay, this is a very important derivation. Okay, it's a 5 marks derivation which they usually ask in your final examination. Okay, so work done in an isothermal process. So let us start with this. So I'll just read out the first paragraph. Consider 1 mole of an ideal gas contained in a perfectly conducting cylinder fitted with a perfectly frictionless piston of area of cross section A. Let the volume of the gas be V, exerting pressure P on the walls of the cylinder and the piston as shown in the figure. Let gas expands and the piston moves through a small distance dx. Okay, so you can see here this is a cylinder. Okay, so this is a cylinder which is of perfectly conducting walls. Okay, and it is a this cylinder consists of frictionless piston. Okay, where A is the area of piston, and this cylinder encloses of 1 mole of an ideal gas. So as you know that when the gas is allowed to expand, so what happens, the gas molecules exerts the pressure on the uh, piston. Okay, so that the piston moves in the upward direction. Let us consider dx as the displacement. Okay, so hence as you know that if dx is the displacement, as you know that the force exerting on the piston can be written as F is equal to Pa. Since P is equal to F by A, so F can be written as Pa. So next, work done in and displacing the piston through a distance dx is given by, which we have already derived, that is dw is equal to F dx, that is nothing but equal to Pa dx, that is nothing but equal to dv. So consider that one as equation 1. Okay, consider that as equation 1. So next, that dv is nothing but equal to dx, which you know that increase in volume, right? So that is nothing but increase in volume of the gas. So next you can see there, if v1 is the volume of the gas, if v1 is considered as the initial volume of the gas and v2 as the final volume of the gas, the total work done can be calculated by integrating the equation 1 between the limits v1 to v2. So see here, I'll just explain once again. We have a cylinder which has the perfectly conducting wall. Okay, and which has the frictionless piston. Okay, where area of that piston is nothing but A. So as you know that the cylinder encloses of 1 mole of an ideal gas. So when the gas is allowed to expand, so what happened, it exerts the pressure on the piston. So due to that, the piston moves in the upward direction. Let us consider the displacement of the piston as dx. Okay, and hence the work done in displacing the piston, okay, can be written as, the work done by the gas can be written as dw is equal to pdv. That is equation 1. So as you know that since the gas expands, what happens is, you can consider, let v1 be the initial volume of the gas and v2 be the final volume of the gas. Okay, so next, in order to find the work done, okay, so dw is nothing but what, dw is nothing but, it is the work done for a small displacement. Okay, so in order to calculate the total displacement, okay, so what is this dw, dw is nothing but, it is the small work done for a small displacement. Okay, it is a small it is a small work done for a small displacement. In order to calculate what is the amount of piston displayed by the gas molecules, total work done. Okay, so we are going to integrate that equation 1, integrating equation 1 with the limits of v1 to v2. Okay, so next, as you know that dw, okay, dw is nothing but equal to integral of v1 to v2 pdv. Okay, that is equation 2 we will try. Okay, so see here, I'll tell you about this w. So as of now we are integrating equation 1. Integrating is nothing but what, you have a little bit idea, right? So the equation 1 is nothing but what? It is dw is equal to pdv. Okay, so here I think there is a small mistake, so it should be dw is equal to pdv, correct? This is the work done, right? So in there is a printing mistake, it has been given dw is equal to dv there. So dw is equal to pdv is our first equation. So we are integrating this equation 1 with the limits. So that is dw is equal to integral of v1 to v2 pdv. So v1 and v2 is the integral. So where v1 is the lower integral and v2 is the upper integral. So now as you know that the standard gas equation, okay, ideal gas equation is nothing but what? PV is equal to mu RT, right? This thing we have studied in thermal properties of matter itself. PV is equal to R mu RT, where mu denotes the number of moles, right? So hence here we have taken 1 mole of an ideal gas enclosed in a cylinder. So the value of mu comes out to be 1 here. So hence the equation can be written as PV is equal to RT, right? That is what we have written here. PV is equal to RT. So taking P on the left hand side and shifting that V on the right hand side, you are going to get P is equal to RT by V. Okay, so P is equal to RT by V. So what we are going to do is we are substituting this value of P in equation 2. So if you substitute that, see here, the integration of dw, as you know that integration of dx is nothing but what? It is x itself. Okay, integration of dx is x. So similarly integration of dw is nothing but it is w. Integration of dw is nothing but w. Okay, so next substituting the values, so the integration of dw comes out to be w, and we have taken RT out of integration. Why is that? You cannot integrate the constant. So R is nothing but what? It is the universal gas constant. Okay, so and what is TT is temperature. As you know that in the isothermal process the temperature remains constant, right? So hence R and T both are constant, so we cannot integrate that. We have taken that RT out of integration. So RT integral of V1 to V2 1 by V dV, correct? So 1 by V dV. So next you can write that as what is 1 by V? Integration of 1 by x. Okay, integration of 1 by x is nothing but it is log x. Okay, integration of 1 by x is nothing but log x. So similarly you have 1 by V there, so obviously it should be log V. Okay, log base EV. Okay, so that is what we have written here. So W is equal to RT log base EV. Limits we have retained the same, V1 to V2 plus C. So that dV will be nothing but it will be a constant. Okay, so here integration of 1 by x dx is nothing but equal to log x plus C. Okay, this is the integration of 1 by x dx. The same thing apply to 1 by V dV, it will be log base EV plus C. Okay, so that is what we have written here. So next we need to substitute the limits. So when you substitute the limits, always we are going to substitute the upper limit first, next minus of lower limit. So that can be written as W is equal to RT log base E. In the place of V you are going to substitute V2. Okay, V2 minus of log base E, again the lower limit you are going to substitute, that is V1. Okay, always when there is a limit we are going to substitute upper limit minus lower limit. Okay, so in the place of V you are substituting V2 and V1 there. So hence the equation comes out to be that as W is equal to RT log base E V2 minus log base E V1. So that can be written as W is equal to RT log base E V2 by V1. Okay, V2 by V1. So next, in order to convert that, there is a log base E, right? In order to convert that one in terms of log base 10, so log base E can be converted into log base 10 as multiplied with 2.303. Okay, you can see here that one. So log base E is equal to 2.303 log base 10. So we have expressed the answer in terms of log base 10. So hence the W is nothing but equal to 2.303 RT log base 10 V2 divided by V1. That is equation 3. Okay. So this is regarding the work done in an isothermal process. Okay. So carefully go through the derivation, go through the explanation first, next go through the mathematical steps. Okay, in case if you have any doubts, please let me know. Tasneem, log value is not 2.303. We are converting log base e to log base 10. So if you want to convert log base e to log base 10, you need to multiply with 2.303. That is what we have done. Yeah, just go through from the starting. Since this is an important derivation which will be asked for 5 marks, just go through. Who is this Rajesh and Ashrit? What were you doing, man? When I said, do you have any doubts in first law of thermodynamics? First, go through the derivation first. Go through the integration, mathematical steps. Just Ganashri, which step you want? So underline the steps which you want me to explain. Yes, Ganashri, underline the step which you want me to explain. Okay, fine. See there, it is nothing but I think integration I have been explained in two chapters, I think, right? One in thermal properties of matter, and yeah, in thermal properties of matter I have explained. See here, it's very simple. We are integrating equation 1 and 2. Sorry, we are integrating equation 1. So equation 1 is nothing but what? It is dw is equal to pdv is the equation 1. So integrating this is nothing but put the integration symbol first, and we have taken the limits. V1 is nothing but what? It is the initial volume of the gas. V2 is nothing but it is the final value of the gas. So hence the integration symbol has been taken from V1 to V2. Okay. So integration of dw is nothing but what? It is w. You can see here in this line, I have replaced the dw by w. Since the integration of dx is x, right? So integration of dw will be w. So next is nothing but what? We have taken R and from the ideal gas equation, you will come to know that P is equal to RT by V. So R and T is constant. R is a already universal gas constant, and T is nothing but what? T is a temperature which is constant in a isothermal process. So you cannot integrate the constant. So we have taken that RT outside of the integration. Left out thing is what? It is 1 by V, right? 1 by V dV. That is what we have integrated. Any other doubts? Okay, fine. Coming to this Ashrit. Ashrit, isobaric test. Sorry, isobaric process is nothing but where the pressure is kept constant. Okay, where the pressure is kept constant, whereas the first law of thermodynamics remains the same. Okay, the internal energy will not be equal to 0, whereas the work done will also be not equal to 0. Okay, so the equation 1, I mean the first law of thermodynamics remains the same. Only the thing is you are keeping the pressure constant. There the volume can be increased, whereas the internal energy can also be increased. That is regarding the isobaric process. Okay, so do one thing. The today's assignment is nothing but practice all the four process of first law of, I mean apply all the four applications of first law of thermodynamics, that is isothermal, adiabatic, isochoric and isobaric. Okay, write down that. Next, work done in an isothermal process derivation. Okay, practice it. When you see it, it will be like, oh, only this much, right? You can do, you will think. Okay, but when while writing in the examination, you will come to know, since you have the integrations there and you have the limits there, you will get confused. Okay, so practice it, practice it. Okay, practice thrice or five times. Okay, practice it until you are perfect with that, since it is a very important derivation. Okay, apart from that, if you have still doubt, okay, even after practicing, if you have doubt, you can let me in the next class. Okay, so just a minute, I'll take the attendance. Okay, fine. Gokul, you have asked the last class recording video. Okay, fine, I'll just post it, I mean I'll forward it in the group. Okay, who is this Ranjini here? Why did you join at the last? What were you doing? You won't get the attendance for today's class. Okay, Ranjini, since you have joined at the last. Okay, fine. With this, I'll just conclude today's class. Okay, so make a practice of assignment what I said. It is very important, and applications of first law of thermodynamics, when you are practicing, practice with examples. Okay, even the examples are very very important. Okay, practice with the examples. Okay, so okay, fine, thank you. We will just conclude the class. Okay, we will meet in the next class.